Now we're going to look at Module 12, Lesson 3. This time we're looking at solids. We've already looked at the kinetic molecular theory of gases and liquids, so we have one state of matter left to consider. Alright, so with this part, we're looking at just the idea of the motion of the particles in a solid. So copy down what's on the screen, and then push play when you're ready to listen. So the particles in a solid are very close together, and because of that, they're not easily compressed either. They're very attracted to each other, which means that if you have a chunk of a solid, and we have the particles of the solid here, if you could look at them at a microscopic level, then it's hard to get them apart. You have to heat up a solid in order to make one of these break loose and come away from the rest of it, which would then of course turn it into a liquid if it could move kind of past each other. Now keep in mind we've had the solids where the particles are the closest together. They are highly attracted to each other. And then you had liquid where the particles can kind of flow past each other. They're very close together like a solid, but they're not in a fixed position. They can flow and they can move wherever they want to. And then of course we had a gas where the particles are spread out, and basically the attractions between the particles of a gas are considered to be nothing because they're not attracted to each other, they don't clump up, they move rapidly and randomly and kind of go all over the container. Now with a solid, a lot of students want to say that the particles don't move, but they actually do. They vibrate in fixed positions, which means they do actually have energy. They just cannot leave this one particular spot and go somewhere else. So that's why we said at the beginning of the year, and I don't remember, I think it was Module 2, that when you have a solid and you put it in a container, it keeps its shape and it keeps its volume. It doesn't change. Okay, let's look at melting point. Pause. Copy this down and resume when ready. So the definition of melting point, of course, is just the temperature where a solid goes to a liquid. And this is not as difficult as boiling point. Simply what needs to happen with melting point is that what's going to happen if you have a chunk again of a solid material is that if you could picture this one right here kind of vibrating back and forth until suddenly it's able to break loose and move away from all of the rest of its neighbors, it's overcoming the attraction that they have to it so that it can leave. Freezing point is the same as melting point, and a lot of people want to go, no, it's not. If I ask students what the freezing point of water is, they'll tell me, of course, 32 degrees Fahrenheit. That would be 0 degrees Celsius. You need to know this in Celsius. So ask them what the melting point of water is, and they'll say 32.1 or 0.1 for Celsius, like just above 32. And the answer to that is no. They are the exact same. At 32 degrees Fahrenheit or 0 degrees Celsius, you can either freeze or you can melt, depending upon whether or not energy is being added. So they are actually the exact same as each other. We're going to look at this more when we look at phase changes in the next lesson. Alright, now let's talk about allotropes. Pause and copy this down, and then you can resume the video when you're ready. An allotrope is simply a substance with two or more different molecular forms. We have already talked about this with network solids a little bit when we talked about the different types of carbon. Right here is one of the allotropes of carbon that we talked about. This looks like graphite. You can remember talking about pencil lead being laid in thin sheets like this, so that as you write, what you're doing when you write with a pencil is you're just leaving the layer that's touching the paper behind. And then you have the actual network solids where everything is linked together. I'm not sure which one of these would end up actually being diamond, but something, for example, maybe this one could be an example of diamond. Allotropes are just different ways to have solids be arranged so that you have different structures, but it also gives them different properties because of how they're bonded to each other. So that can actually change the properties of a solid. Alright, and these are kind of fun, which is non-crystalline structures. Pause for just a minute and copy this down and resume it when you're ready. You have these amorphous solids, like the examples that are right here, rubber, plastic, asphalt, and glass. where if they're broken, they don't have an ordered internal structure. It's almost like they're somewhere between a solid and a liquid. They don't know exactly which one they want to behave like. And if you're thinking of glass as being like, there's no way that this is not a solid, glass is definitely a solid. No, not exactly. If you look at very, very old windows, if you could look at them from the side, like take them out and look sideways, instead of being pretty much the same thickness for the panes all the way down, you'll see that they can actually look a little bit wider at the bottom and kind of skinnier at the top, because over time gravity has pulled them down, and they start to get pretty wavy, and they don't look real nice to look through anymore. Think about like Old Salem, maybe the Biltmore, places that have original windows. You can see that they aren't exactly nice and flat and smooth anymore because they're amorphous. I'm going to include a link on this lesson to a video where you can watch people messing around with cornstarch and water because it's an amorphous solid. If you mix it together and you put a lot of pressure on it, it acts a lot like a solid, but if you go real easy with it or just kind of hold it in your hand, it oozes like a liquid. And so you can get an example of a real-life confused amorphous solid. From here, it's practice time. So check out the YouTube link for the cornstarch, for the amorphous solid, and then try the practice problems on your sheet. We will go over those when you get the answers, and if you have questions, you can let me know.